Thank you very much for the introduction, and thank you very much for this opportunity to talk about oncology in this context as well. I want to talk about a very particular type of pediatric brain tumor, diffuse midline glioma. It is a rare type of brain tumor that only occurs in a couple of children every year here in Switzerland. But the implications of these tumors are still tremendous. It is a type of glioma, meaning it is intrinsically already a hard-to-treat tumor. But as you can see from the name, it is also a diffuse and infiltrative phenotype that is located in the midline structures of the brain, such as the thalamus and also the pons. And these structures really control vital functions. And so you can imagine if you have a tumor in these regions, that is a very poor prognosis, and it is a tumor that is also very hard to treat. And because it is so hard to treat, we also have very poor outcomes overall. So median overall survival for patients with diffuse midline glioma is typically is less than 1 year, which is even less than other high-grade gliomas which are located in the hemispheres. And what this project actually was looking into is one of the major lines of treatments for pediatric diffuse midline glioma, which is radiotherapy. I'm now at the University of Bern, where I lead a Center for AI in Radiation Oncology, and I think this is really a great use case example where we could hopefully really make an impact by improving this kind of treatment for our young patients. I'm showing you here some MRIs of a pediatric diffuse midline glioma case, where I hope you can appreciate kind of this hyperintensity in the pons. The idea is really that we would like to tailor a treatment, and in this case, the radiation, to these individual patients more specifically. And I will talk about how we want to achieve that. I do want to emphasize, though, that this is only one part of the treatment journey of these patients. And in the end, if we want to really make a difference for an infiltrative tumor, a localized treatment such as radiation, of course, will not do the full job. So in the end, a lot of the research that we also do in our group is actually looking into systemic therapies to support this. But I will not talk about that today. I will talk about imaging. Because MRI is really the cornerstone of diagnosing these patients and also to make a clinical decision regarding the treatment. And actually, it is also largely the basis for the planning of the radiotherapy. For radiation, we actually create a treatment plan for each particular patient. This is not specific to children. This is really each patient receives a personalized plan where we shape the dose distribution specifically where we would like to achieve that. And so what this means is that the image really is the basis for the calculation of this treatment plan, and at the same time, it's also the basis for the response assessment. And I'll talk about that a little bit more. So what this means is that I think predictions, and I will talk a lot about AI here as well, of course, but they should be done in the domain that is most relevant clinically, and that is the imaging domain. So if we could provide a prediction of where a tumor is likely going to progress to on an image, we could use this information to inform our radiotherapy treatment planning. And this is very specifically for the parts on the image that we do not yet see. Radiation accounts for the gross tumor volume. So that is the part of the tumor that you actually see on your image. But on top of that, we all know that these tumors also have a microscopic infiltration. Most tumors actually have that. And we need to account for this. And then on top of that, there's the third one, which is the planning target. This is just geometric uncertainty. I'll not talk about that. But how can we account for something that we currently do not see? Of course, there's guidelines for this. This is a guideline in an adult case because I think it was showing very nicely what is currently being done, and that is an isotropic expansion on the order of centimeters in some cases, just beyond what we physically see. And I think we can all appreciate that, of course, tumors do not grow isotropically necessarily in the brain. There are certain anatomical barriers that are considered for this, but still, this is a huge simplification that we could easily account for with more informed models of brain tumor growth. So here, if we had an estimation of the area of the growth, we could actually adjust these margins specifically also for the individual case. I do want to emphasize the second use, though, of providing anatomical growth predictions in the form of images, and that would be the use in the context of synthetic controls. In pediatric applications, of course, it is very difficult, if not impossible, to run randomized clinical trials. If you now think about a rare type of brain tumor with a very poor prognosis, and your child would be randomly selected into the control group, of course, this would not be very ethical actually to conduct. So a lot of these trials actually rely on retrospective data as historic references. And here what we could provide is actually a synthetic control, so an estimation of how a patient would potentially look like under the standard of care or in the absence of a treatment as well. And I do want to motivate that this is not something that is potentially very far from the clinical reality, because there are actually some nice examples already in the adult domain where this is already being conducted. This is a study which was published in 2024 about an AI-based prediction model of glioblastoma recurrence. They used a deep learning framework in order to predict the heat map of the most likely anatomical location of the tumor regrowth after treatment. I should stress that these tumors receive surgical resection, something that we do not do in diffuse midline glioma, but it is the same type of concept. There is a prediction, and we then want to use these predictions in order to target our radiation fields specifically here. This is a figure from this publication actually showing that there was a good correlation or co-association more closely between the predicted location of recurrence and the location where the recurrence actually occurred. And the reason why I wanted to bring this up is because there was a very recently studied clinical trial now that was conducted based on this publication. It was a phase 1 study, so of course the primary endpoint here was not necessarily efficacy, but they did quantify progression-free survival as well as overall survival in 2 groups. One was a standard of care, and this is actually a retrospective control group as well, so it was not a randomized trial. And the other one, that is the blue curve, is a personalized radiotherapy approach, where they gave a specific radiation boost to these regions where the tumor was predicted to recur. And they actually observed a significant, even in this small subset of patients, improvement in progression-free survival and overall survival. This sounds now almost too good to be true, and I do want to emphasize there are some strong limitations also to this study. It is phase 1. There was also significant toxicity reported, and this really still needs a lot more emphasis to be rolled up. But I think it's a great example of showing us how we can use predictions in the imaging domain to translate to really something actionable also in the clinical application. And I do want to make a second point about response assessments on imaging. Actually, currently in the clinical practice, response is assessed predominantly on axial measurements. So you do consider multiple contrasts. So we have multiple contrasts in the MRIs, but we take the maximum diagonal axis on a slice, and then we compare this pairwise across 2 time points. And if the increase in area surpasses a certain threshold, we categorize this as either progressive disease. If it goes below, then it is a controlled case, or of course there's also the in-between, which is a stable disease. So it is really simplifying a lot what is an overall dynamical process. And this was now recently also much more accomplished or appreciated, and there have been a number of review articles where it's really about how can we use AI in order to improve response assessments on imaging, using AI tools to volumetrically segment tumor volumes to provide longitudinal context, and thereby also open up the floor for tools such as synthetic controls to be used more specifically also in pediatric applications. And I did want to show this example here, which I think illustrates quite nicely a few problems that we have if we're just looking at a pairwise comparison at a fixed time point, and that is the onset of possible pseudoprogression after radiotherapy, meaning that the tumor initially appears to be enlarged. Yeah? This is not necessarily a real growth of the tumor, it is just also potentially edema. Then there's another regression in the image, and then it grows back. And I hope you can also appreciate, yes, these are 3 different segmentation tools. They do not all perfectly agree with the manual segmentations that were performed here, but the overall trend in this longitudinal trajectory is captured just equally well here. And I think this shows very nicely that 2 things should actually come together, and that is the longitudinal accounting for the trajectory of a tumor as it responds and regrows after therapy, as well as the spatial information in terms of where is this recurrence, and for that we need the information from the image. And so this is now where this project actually comes in. We wanted to develop a model that would provide such predictions. And of course, for any type of data-driven approach, yes, we need a lot of data. A lot of data is also available. This is quite multimodal potentially. We focus here, of course, on the imaging information, potentially also on the radiotherapy treatment plans. But if we work with pediatric applications, and I'm sure a lot of you know these limitations, there are some restrictions usually in the data that we work with. Data is acquired longitudinally. This is not specific to pediatric patients, but this is just specific to the clinical context. And there's never a perfect time that everyone has to scan 3 months after radiotherapy, for example. So we need to account and be flexible with our models to be available with also different imaging schedules. There's a lot of missing data. Typically, data is never really missing at random. There's a good reason why some information are available and why some are not available. And generally speaking, if we deal with pediatric populations and a rare type of disease, the size of the data is always too small for what we would like to do. And on top of that, if we try to pool data from multiple institutions, we have to deal with very heterogeneous sources of data, very heterogeneous sources of images as well. And this was also the case that we were facing here. It's a large international consortium from which we pool data across the globe, really. We have collected a really nice data set by now that we want to harness in this context. But how can we account for this temporal aspects and the missing data potentially in this context as well? And here's where I wanted to talk about math. And I'm really glad that we had the first talk of this day already introducing the concept of mechanistic mathematical models. Because I also agree, I feel sometimes now in the whole realm of AI solutions, and they can do great things with data-driven approaches, sometimes I think these models fall a bit short or are underappreciated. And I do want to make a point that actually there's a lot of synergies potentially between data-driven and mechanism-driven approaches, where we try in the mechanistic models to incorporate our current understanding based on simplifying assumptions. I think this is very important to state also here again. No mechanistic model, or maybe at some point, but for now at least, is ever going to capture every single detail down to the really underlying atomic structure, let's say. So we always have to find a model that is as simple as possible and as complex as needed for the approach that we would like to address. The advantage is, of course, though, that mechanistic descriptions can live on, for example, more sparsely sampled or irregularly sampled time series information to make a prediction of growth, for example, of tumors. At the same time, data-driven approaches, which live on this parameterization, and we don't have to have this prior understanding of how a connection between the input and the output would come to play, are very flexible. And so in between this, there's this concept what we tend to call mechanistic learning or knowledge-informed learning. And there's multiple facets of how we could incorporate these mechanistic priors into the learning concept. And I do want to talk a little bit about some different options of how this could be achieved in the context of always looking for oncology applications here. The easiest thing of how you can combine two things is you do one and then you do the other, right? So a sequential combination. A great example in this context would be you predict a mechanistic parameter of a model. For example, a tumor growth rate from a molecular profile of a patient's tumor. Or you can do a sequential approach of a tumor growth model and then generate an image. This is the example that I will look into in a bit further. What this achieves, of course, is a greater interpretability overall because the mechanistic part usually is much more approachable. And you can account for these differences in sampling of the data as well. If you can do sequential, of course, we can also do parallel things. And this is usually where we want to account for the shortcomings of one method or the other. For example, we can produce surrogate models to improve computational efficiency. We could use symbolic regression approaches to learn mechanistic equations from the data. If you want to go a step further and actually see how could we synergistically also combine these in order to improve our current understanding, I like to bring this example of digital twins. I mean, everyone here probably even has different definition of what is a digital twin. It can be a mechanistic version, there can be data-driven approaches. I would suggest we could use parts from one or the other put them together to build a complete picture in this context. And of course, I think this is the actual combination, intrinsic combinations, where we really build mechanistic understandings into the architecture or the training process. For example, biology-informed neural networks, where we use, for example, graph-based architectures informed by protein-protein interaction networks or gene regulatory frameworks, where we directly constrain the architecture to known interactions. Or we could have physics guidance. I don't know why we call it physics and biology. I think it's not separated by these techniques. But we could constrain actually also the loss functions to mechanistically inform priors in this context. I would like to give now one example of a mechanistic learning framework where we actually use a sequential approach that combined a mechanistic model of tumor growth, so tumor area or volume over time, with an image generation model, so a diffusion model that generated us an MRI image of that particular tumor at a given predefined size of that tumor. And this is work being conducted in my lab by Daria Laszlo and Eftemis Georgiou over the course of this project. What we actually wanted to achieve is to quantify how realistic can we generate these images. And we didn't want to use just a typical benchmark in terms of metrics. There's a lot of metrics we can calculate. I'll also show you some metrics. But we really wanted to go a little bit deeper, meaning to understand how realistic are these images to human observers, and do these predictions actually also anatomically grow in the directionality where the tumors actually progress to. And as I mentioned, this is always a limited data problem. I'm showing you here the study that was actually predominantly trained on public adult data, hemispheric glioblastoma data, and then we had a smaller subset of patients that we used to refine this, and this included diffuse midline glioma patients. And on top of that, we then have a private test set, showing here examples only for a subset of the data that we actually have, where we have longitudinal information then available that we can use to quantify the agreement between the prediction and the true progression. And so these were some of the images very early on that we actually obtained, where we could predefine a certain growth threshold. We optimized here for these 20 to 25%, which is this typical response assessment cutoff when we would kind of change the classification towards progressive disease. And of course, we can also visualize the differences between the original image and then the generated one at a larger size. Nice thing is that we can actually repeat this process multiple times and therefore obtain a probability distribution rather than just a single image. And then, of course, we can also stack these to obtain a three-dimensional volume in terms of a prediction of where volumetrically this tumor is likely going to be extended towards. So now, to us, and we were no radiology experts, it looked pretty okay, right? It seemed to grow asymmetrically, yes, okay, so let's see how realistic actually are these images. And this is where I promised you some numbers, right? So these are typical metrics which are used to quantify image realism in the context of benchmarking of these types of models. Some of these metrics are actually very sensitive to the size of the data, so you have to keep in mind that this can be accounted for. But roughly speaking, actually, we had pretty good performance. So this was okay, this was not amazing, but I think the performance here was to a state where we were saying, like, okay, this is a very good first attempt. But we wanted to go a little bit further, and so we did a user study where we asked some radiology experts if they could tell us if, when presented with a specific image, if this is a real one or not. We had some radiology board-certified neuroradiologists, and then we had some of their fellows as well considered here. I want to stress there was no difference in performance between fellows and experts. They all did equally bad, actually, on this task. So they were not able to differentiate, and we had actually a large number of scans that were presented here between, and it was perfectly balanced, I should also stress, actually, between the real and the generated images. However, I'm also showing you here the blue one, which is actually a unit that we trained just to do the same task. And actually that unit, it's not amazing, but it's certainly better than random. When we looked into what kind of features are actually driving this distinction between the real and the generated images, we actually found that this is underlying noise levels in the images, which are much smoother in the generated ones. So while this is something potentially we could also account for in the generation process, I think we have to, of course, see what context do we want to apply these images. So I think something to consider when we want to use this, for example, as synthetic data to retrain, we have to be aware of this. For now, we will continue because the noise level in itself, for our human observers at least, was not something they could pick up. We actually went a little step further with a study together with the University of Applied Sciences in Brugg, with Professor Asu Kötikin, where we did eye tracking on a larger set of people, this time not only medical experts, but also AI experts, and repeated this experiment, looking into real and generated images, once just presenting one image and once showing side by side, real and generated, and they just had to judge if it was left or right, which one was the generated one. And it was nice to see that actually also in this context we could reproduce that if users were presented just with one image, they were not able to distinguish these, neither the AI nor the medical experts. However, if shown side by side, still the majority of people couldn't tell, but there were actually a small group of people that actually saw differences in this context. And if we looked at their attention maps in terms of where they were looking, it was usually very specific regions of small hyperintensities. It is still an ongoing assessment of these attention maps, but I thought this was actually a very interesting finding to go back and see actually where does the human look. So how could we quantify what humans are looking for in terms of judging the realism of a specific type of data. So now that we had established that at least the images look realistic, they seem to be computationally in terms of the metrics realistic, we of course also quantified the longitudinal extent. For this we actually used 180-ish slices from a previous scan and then also the follow-up image and calculated the agreements in terms of dice coefficients. A dice of around 0.8. This is not perfect, but I think it was in this context good enough for what we wanted to see. And if you look at some specific examples, it was also really nice to see that the directionality actually was also captured quite well in these models. So now you may wonder, should we have stopped here? I left out an important part, right? And that was the time factor. And this brings me back to this mechanistic combination approach here, because for now, all we did is predict an image at a larger tumor size. But we actually wanted to predict an image at a future time point. And so here now we combined this mechanistic tumor growth model to make a prediction about the size of the tumor at a later time point, to sample from this distribution, and then obtain our growth probability maps again. And this mechanistic model is actually inspired by Anna's thesis. Anna did her master thesis on a spheroid-based project, also in diffuse midline glioma, spheroids, small cell structures in a dish. And she actually developed a mechanistic framework that we could use to trace a variety of different trajectories that we observe in these tumors. It was an ablation study to also minimize the complexity of these models. And what we ended up with was a parameterized version that uses only 4 parameters in the end, of which a lot of these actually we can also make them constant at the population level. It's an exponential tumor growth model. I know tumors don't grow exponentially, but in the context of the assumption that we're making here, for a short time frame, we will approximate this with an exponential behavior. We then calculate our treatment effect and summarize everything that is being done in this context into one variable, which is a surviving fraction, where we compartmentalize into a surviving and a future dying compartment based on this parameter. And we have new dynamics for this decaying compartment with a different growth rate, lambda star, which actually in this case followed a tangential, a hyperbolic tangents distribution, so a sigmoidal shape going from growth to shrinkage in the end. And this model actually, we could show that it was designed on these spheroid trajectories, but it actually worked also very well in the true DMG tumor trajectories. And so then we went on and we actually did what I was talking about before, that we sampled from this distribution where we held the last point out in such a prediction to make then a prediction about the estimate of the size and then sample from that. And what we then quantified was actually the directionality, but also again in terms of Hausdorff distance or dice coefficients, the agreement between the predicted and the true growth in these tumors. And this is what I'm showing you here, relative between the generation with the true size and the estimated size. And these are some of the probability maps that are obtained in this context. Probability maps certainly in terms of the absolute values look a bit different, but the directionality, again, was consistent. And that actually led also to consistent evaluation in terms of this Hausdorff distance. I do want to stress this is a project that is still ongoing. It is a project that originally started with my PEP fellowship here from the BRCCH. And we very much look forward to building this now into a larger project that actually goes more into this intrinsic mechanistic combination, where we're also incorporating now the actual dose distribution in this full context. So with this, I would like to conclude. I hope I could show you some motivation of how we could tackle the general problems that we often are faced with when we work with data-driven solutions in the context of pediatric applications. Here I wanted to make a case about a particular rare type of brain tumor that really has a strong unmet need to improve the outcomes for these patients, and to make a point about how we could potentially combine mechanistic modeling with data-driven solutions. Thank you very much for your attention, and I do want to appreciate that this is not just my own work, but actually it's a whole team working on a variety of projects in the context of DMG and radiation oncology. Thank you.